Here's the usefulness of a Ka and Kb value multiplying together to equal 1 times 10 to the minus 14. If you have a weak acid like HX, and that acid reacts in water, like acids normally do, and make hydronium and X minus, of course there's an equilibrium constant for that acid, and in this case I just made it up that it was 1 times 10 to the minus 4. Now, of course, the Ka value pretty much tells you the strength of the acid. As the acid gets stronger and stronger and stronger, there are more and more products, so therefore the Ka value should increase. In the case of a strong acid, since it goes to completion, the Ka value is pretty much positive infinity. But the main point to this is that as the acid gets stronger and stronger, the Ka values get stronger and stronger, larger and larger, and the Kb values, likewise, will have to get smaller and smaller. The stronger the acid, the weaker its conjugate. And that's the deal with the hydrochloric acid. It has such a huge Ka value that the equilibrium constant for its conjugate ion, Cl minus, is basically 0. And that's why chlorine does not hydrolyze in water. The other usefulness of the Ka and Kb values is that if you did somehow have a negative ion, a source of this negative ion like X minus, and you put it in water, since X minus is the conjugate of HX, it will react and make OH and HX. And you can find out the Kb value for this reaction just by looking at Ka and Kb should multiply together to equal 1 times 10 to the minus 14. And so some salt that contains this ion should react in water since its conjugate is a weak acid.